Okay, so this data set, probably you guys have already seen the air passenger data set. So if you just run this, you'll get that this is one of the oldest data set, as we said, and we have worked on this particular data set. We have used simple linear regression technique with feature engineering like trend and Fourier transformation for basically all kinds of ML and statistical machine learning technique. But whatever we have tried so far, and with that we did a pretty decent job. Up to we have reached up to like 90%, a little even more than 90% in the out of the sample accuracy. But whatever we do, all these simple model always assumes that each of my instances are independent. Okay, and we know at the at the core that time series instances are not independent. So it shows that even if your model is breaking a core structural issues of a problem where independence is a bad assumption, even with that bad assumption a model can do it decently well, right? So this is an example that with a bad assumption a model is still doing decently well. So these kind of model can be used as a baseline model, and obviously after taking the baseline model, if you can try to develop a model which does not make such kind of bad assumptions where instances are all independent, in those cases you will have a much better model. Like you should expect that your model will be doing better than the existing this kind of simple linear regression model. Now if you take the plot, this piece of line basically do a plot of log scale, present the air passenger model in a log scale, and we see that now in the previous plot clearly you can see the scale is increasing at an exponential rate. So now that means whatever model you assume, the variability of your data was increasing with the time. But when I'm taking a log scale, in the log scale your variability is sort of now stabilized. So homoscedasticity assumption is probably will be correct if you make a log transformation. And my experience, as I said earlier also, that economic data, population science data, epidemiology data, if you take log transformations, generally they do pretty well. Now here is the piece of code on TCS data from the internet. So when you are running this piece of code, you have to make sure that you are connected to the internet. So let me just run this T-series package and QuantMod package. Now this piece of code will draw the data from Yahoo Finance. This is in part of the QuantMod package, and you can see that there is a tcs.ns thing, and the data is being downloaded from 2nd January 2007 till we don't know 15th Jan 2024. So till yesterday, today is 16th Jan, till yesterday all the data was downloaded. Okay, now I'm just taking the adjusted close price in this case, and if I plot TCS, and then this is how the TCS close price look like, adjusted close price looks like. And again, if you just plot log of TCS, it will give you the adjusted close price. And as I see that obviously 2008, when you had this huge Lehman Brothers crash, that time there was a huge crash in the market, in the stock price, and then it boomed back and kind of grew at a steady state in exponential compounding exponential growth is being experienced in the TCS stock. Being a large company, it experienced that kind of effects. Now here was the Johnson & Johnson data set. I just printed the data set. It's a quarterly data set. Each quarter, what is their profit per share. These are like cents per dollar kind of, or per share value or something like that. And then if you plot that, so you can see that during 1960 to 1980, Johnson & Johnson's profit per share was growing at exponential rate. And if I take a log transformation base 10, we see the similar pattern, that it gets stabilized, and we see a log linear trend in the Johnson & Johnson's profit per share. Now, next example, we discussed that US population. This data set is, if we go to question mark, US pop, in dataset, base datasets package, you have this US population as recorded by the US census from 1790 to 1970. Okay, so if you see that, we see that, as we said, that it's kind of going up, and then when we plot this, we see a kind of a slightly increasing at a decreasing rate kind of situation, particularly after World War II. During the World War, there was a quite a flattening time. These 5 years we are seeing, and then it's kind of started flattening out. It will be fun if you guys can get the data till date and just plot and see that more flattening effect you will be able to see now. Because so what's happening in the US population is they have grown into a very developed stage, so where they have enough money. So they are, when a country grows to have enough money, a prosperous country, prosperous nation, obviously generally what happens, the population growth rate comes down. And as I said earlier, as I discussed earlier, typically in the population science, replacement rate is 2. Like 2 parents, if you are replacing 2 parents by 2 children, then your population is not growing, population is not declining, population at a stable rate. Interestingly, in US, what happened is, if you look into the birth rate is below 2. So based on birth rate, their population should have declined, but their population is not declining, population is stabilizing. It's stabilized. Main reason is they do allow migration. So immigration rule is very progressive compared to the other countries. As a result, so whatever the gap, that gap is replaced by the immigrant population. So this is what is happening, and it will be fun to, if you guys can, I think somewhere their data is definitely available, at least census data definitely available. You guys can download and just plot and see what is happening. That will be fun thing to fun thing to try out. Here is the piece of code for daily COVID-19 cases in India. Let me see if it is still there. Okay, yeah, it still downloads. Fine. Yeah, it's working. This is the data sets from where I'm downloading the data. I don't know whether what is the latest data set that they have. Let us see. I am downloading the data and let me see state-wise data. So from 30th January 2020 their data started. So 22nd August 2023 till 22nd August 2023, I think after that they stopped probably. So now they are not collecting the data. So but you have decently large data till August, 4 months back, the data is there. All right, next what we can do, we can do a state-wise okay, so the data came as a, the date string came as a string, so I had to convert it. So this piece of line is converting the date string to a date format. Okay, and then cases for the India, I have converted them into the TS time series object. So this TS, if you question mark TS, so it is time series object. It's a data type. In R, TS give you a time series object as a, basically it's a different data type like list, array. Similarly, you can define time series as a data type. It's a, here TS is, you can think of as a, they are calling it a time series object, but effectively in all practical purpose you can consider as a time series data type. Why? Because you need, in time series you need a indexing, right? You need a indexing. It could be date, it could be time, it could be hour, it could be minutes, seconds, whatever, but you need some kind of indexing of the data, so that the order is very important in time series, who coming before whom and who is coming after whom. So that information need to be stored very accurately, and that information will depend on the year, date, month, day, time, hour, minute, seconds, day of the week, month of the year. All these information need to be stored, right? So time series object handles all those information nicely. Now if I run this, okay, I did not run this piece of code, let me just run that, and then yeah. So what we are seeing here, as we discussed last time, this was the first wave, this was the second wave, the really nasty one, then the third wave, very short-lived, fourth, and there is a fifth bump. And many of us were not even aware that there was a fifth wave. I mean, some of us have heard about it, but when we plot it in log scale, log base 10 scale, now it is absolutely clear there was a fifth wave. In 2023 there was a fifth wave, and there could be a sixth wave as well. I mean, we cannot really completely ignore this, but there is a good chance that there is a sixth wave coming, or may have come and gone, we don't know. Here is the links trappings data set. Let me just, between 1821 and 1934, annual number of lynx trapping for 1821 and 1934 in Canada. This is the source, Brockwell and Davis, 1991. This appears to be a series considered by Campbell Walker in 1977. Now, what is lynx? If you just Google it, so you can see it's some sort of cat, but it's a slightly bigger cat than a domestic or typical cat that we see. It is slightly bigger than that. Okay, and so these trappings, obviously, when the number of lynx will be increased, the hunter will go and the tappers will go and trap them so that their population can be checked. Otherwise, they will come to the urban areas or the towns, and then it will be more of a mess. So if you can see that, let me just increase this size. So these are annual number. Remember that these are annual numbers. So 1840 to say 1816, 20 years time, like every 5 years looks like there is a cycle. Seems like there is almost like a 5-year cycle. It is going up and coming down, going up and coming down kind of thing. Okay, we don't know exactly what is the cycle. Sometime it could be 6 years, sometime it could be 5 years, sometime it could be 7 years. But 5 to 6, 7 years is the cycle that we can see. Like between 1820 to 84, there is a 2 cycle. There is 1840 to 1860. There is a 2 cycle. Between 1860 to not 5 years, it's a 10 year, right? Because in every 20 year, if there is a 2 cycle, that means every 10 year 1 cycle. So the periodicity is approximately 10-11 years, right? Yeah, so my mistake. So it is, the periodicity is about 10 years of periodicity, a decade of periodicity we are seeing. So this is, and so what we are seeing for in the air passenger data, the periodicity we knew exactly 12 months. But here, in this kind of data, we don't know exactly what would be the periodicity. Periodicity we know from the data looks like 10 years, it could be 11, it could be 9, somewhere 10, a decadal periodicity. Okay, so this is an interesting phenomena. Then monthly sunspot. So this is the monthly sunspot data. So sunspot from 1749 to till date, actually saying that till 2000 it has there. Now if you run this, so you can see this little, let me just clear it, and so you can see that it is, this is one of the advantage of in R, if you save it as a time series object, and you can present the data also in a nice format. Like you can clearly, this is a nice presentation. Inside the data is stored as a vector with all index informations. Okay, but here what we have is, it's nicely presented. Now if we look into, it's a monthly numbers, and if you look into the plot, let us increase the size. Now what we are seeing, between 1750 to 1800, So 50 years time period, how many? 1, 2, 3, 4, 5, 4. And then between 1800 to 1850, another 50-year period, 1, 2, 3, 4, 5, 4 to 5 cycle we are seeing. So again, it is not clear we will be in a 50-year period, we will be seeing a 4 cycle or 5 cycle. So if it is 4 cycle, it will be about 12 years of period. If it is a 5 cycle, it is a 10 years of period. So maybe periodicity is around 11 years. We don't know. Okay. So again, certain physical phenomena, we don't know what is the exact periodicity, but from the data can we estimate the periodicity. Okay. If we can have the periodicity, obviously we can do a lot more. We can estimate, we can model, we can forecast, and all these things a lot better. Okay. Next, New York air quality data. So daily air quality measurement in New York between May to September 1973. So it's a daily data of May, June, July, August, September, about 5 months of data of 1973. It's a multivariate time series data, by the way. You can see ozone, solar, wind, temperature, month and day. Okay, so it's not a, so you can go month and day is there, and every month, every day you have all these observations. 4 observations are being observed. So it's a multivariate time series data. At a given time point, you are not observing one particular variable, you are observing 4 variables. So it's a multivariate time series data. Obviously, there is a temporal or time-wise dependence, and then there you should expect some cross-variable dependence also. You can expect that maybe wind and temperature or ozone and temperature, they are correlated. But at the same time, that correlation might be effect because of the time. So it's a bit of a, so you have to be very careful who is influencing whom. So because of the time also, that correlation, a particular time, the correlation might increase at a, so that correlation that you are seeing, is it because of the time or is there really a correlation? So sometimes we may have to figure out how to remove the time effect. After removing the time effect, can we, is there still a correlation between the variables? Then we can say that yes, even after removing the time effect or time dependency, if we see that yes, there is a correlation, then we can say that yes, there could be a possible correlated effect between the variables could be correlated. So this is the, you can see that there are a lot of layered complexities are there in time series data, and these are not straightforward, statistical machine learning kind of problems. So we have to handle these issues very carefully. So these issues are not typically get handled in a typical standard regression framework or a machine learning, like decision tree, random forest kind of framework. In those framework, always we assume that the data is the cross-section data, so each instance is an independent. But once I am going out of it and going into a time series kind of scenario, and I am assuming that because of the time all my instances are correlated over time through index. Now I am seeing these, say, ozone and time, temperature, right? Suppose I'm taking ozone and temperature, and if you just take the variables column ozone and column temperature and calculate the correlation, you may find a correlation. Highly possible. Now you remove the time effect. Somehow you figured out, I'll show you in the future lecture. Suppose you remove the time effect. Once you remove the time effect, this correlation may disappear. If this, after removing the time effect, if this correlation disappears, that means the previous correlation that you just got between ozone and temperature, that was a spurious correlation, right? Example of spurious correlation, say if you take say revenue collection of Chennai metropolitan area and garbage collection of Chennai metropolitan area over the year, you will, and if you just calculate correlation, you will see very high correlation, right? Now if you remove the time, and you may see that there is no correlation. Why? Because over the time population has grown, and because the population has grown, both the revenue collection and the garbage collection has gone up, right? So there is a third latent variable which is causing the correlation between your revenue and the garbage collection. Now this, and that is happening because over time. So there will be the population is going up over time. So once you remove the time effect from the revenue collection and the garbage collection, whatever residue effect you left with, that residue effect should, if they are correlated, correlation should be there in the residue effect. But if there is no correlation in the residue effect, then you can say that okay, these variables are not necessarily correlated. The correlation that we are seeing is just because of the time. So you have to be, in a time series data, you have to be very careful about spurious correlation. The correlation, just if you take a time series data, take two variables, calculate correlation, if it shows high correlation, there is a very good chance that correlation is spurious correlation, meaning meaningless correlation. So you have to be very careful when you are saying correlation between two variables calculated from a time series data. You have to be very careful whether they are really correlated or they are just demonstrating a time effect or trend effect, rather say trend effect. Okay, let us go to the next thing. So you can see there are some missing value. Let us see one more time how the ozone data look like. In the ozone there should have been some missing value. In the ozone, yeah, there is a Na, yeah, Na, yeah. Correct. That's why, yes.
There are two variables in time series which are moving together through time and we are seeing correlation in that. Shouldn't we consider that to be valid correlation?
Now that movement could be just because of the time and because of another third variable. So like I said, the revenue collection and the garbage collection of Chennai metropolitan area is just manifestation of the increasing population over time in Chennai metropolitan area, right? So if in the Chennai metropolitan area population get stabilized, right, and so naturally what will happen, revenue collection and the garbage collection will get destabilized, and then the correlation will vanish. So the now what you are seeing, the correlation, they are moving together because of the trend effect, not because they are actually correlated. Okay, so that is where that is the point I'm trying to make here.
How do you distinguish? How do we know if it is actual correlation?
So that the question we will investigate over the course basically, and you will see that how can we figure these things out. Okay. Next, so if you plot a grid here, it's 8, okay. Now, next is Nile data. It is also another very old data. So, measurement of annual flow of the river Nile at Aswan, formerly known as Aswan, 1871 to 1970. Between 100 years, annual flow is being recorded. And annual, if you plot this data, you can see that annual flow was at a certain level, and then around 1900 it came down significantly. The overall flow came down, and that was because of a dam was put in on the Nile, and also. So to investigation, often people use that, if you want to put up a change point problem, then if you want to estimate exactly what time the change took place, as if you are pretending you don't know when the dam was put in. Now, can you identify that change point? So that's the one problem that you want to figure out. And then obviously because of the dam, whether the volatility has gone down or not. The before that probably it was a lot more volatile, another thing, and after the dam, because now it is well regulated, the overall volatility should be reduced. So these are the two problems, most popular problems that people try to figure out. Now this is another data set, discovery data set. So great inventions of scientific discoveries in each year between 1860 and 1959. So about 100 years of time frame, and so this is the data set that you can get. All right. So this is the Johnson & Johnson dataset we have already discussed. So there is a TSA3.RDA data which is also available in the GitHub. I will also make it available in the Moodle. You should not have any problem. Global temperature deviations. Now GTemp. GTemp could be, I think, is a part of this particular data set. Wait a minute. Yeah. And now, yeah. So GTemp is a global temperature deviations data set. This is a part of this RDA data set that come with, I think, Shumway-Stoffer's book. This is also available, I think, somewhere in the GitHub, in the open source. So I'll also share this link to this data set, should not be a problem. So this is the deviation temperature from the original data, so it is not the actual temperature. So even the deviation is rising, so it shows that you don't have to be, it's really alarming situation to a great extent. Now speech data set. I think speech data set is also time series data that we discussed. So the word ah was, the sound ah was kind of recorded over 1/10 of a second, and then 1/10 of seconds were recording 10,000 hertz, and in 10,000 hertz only 1/10 of that is being presented. Here it shows that when we pronounce a word, it is a much more complex activity or complex systems. This thing actually shows that complex behavior. All right. Then this is the stock return, or not stock return, S&P 500 return of New York Stock Exchange, and I think this was the 1987 crash moment, sort of. Now this is the El Nino and fish population data. So this is the Southern Oscillation Index and new fish recruitment, the number of new fish that was recruited. So when the number of new fish goes down, that means diversity in the ocean has gone down, and the new fish goes up, that means the diversity of the ocean has gone up. And question is whether Southern Oscillation Index and the fish diversity, they are correlated or not. Obviously what we are seeing is it has a different frequency behavior and this has a different frequency behavior, but question remains whether they are correlated or not. And obviously if it is correlated, in which direction they are correlated, right? In Southern Oscillation Index, obviously if because of the rising temperature, is the ocean diversity, fish population diversity increasing, or is it really decreasing, and only one species or two species is kind of dominating the entire ocean? If that happens, that is not very good for the entire world, right? So because ocean, remember that ocean is the 3/4 of the entire world, and we would like to preserve, we would like to see that the ecosystem is stable in the ocean. And now here is the earthquake data and the explosion data. So this data was the earthquake data, the seismic activity of the earthquake data, and this data is the seismic activity of explosion, how explosion. So clearly physical, signature is completely different. You don't have to do any kind of analysis, just visual representation will tell you, okay, yeah, this is a earthquake or this is a explosion. So up to this, that's all I had. This is what we discussed last lecture, and So I think next we will start actual theory with hand theory next lecture. Let me stop here.